Artificial Neural Network, or ANN, are the backbone of almost all AI models widely used these days. They include large language models like GPT, Llama, and Gemini, and hundreds of other narrow AI models for image processing, robotics, predictions, and classifications. This short video explains ANN architecture and how they are trained in a layman understandable manner, such that business users like you can grasp how they work and make the best use of these technologies in your daily business operation. ANN is a machine learning program or model that makes decisions in a manner similar to the human brain, using processes that mimic the way biological neurons work. Here, you can see that the artificial neuron, or node, and synapse on the right have similar structure to the human neurons on the left. ANN is normally composed of thousands, or even millions of neurons. Here's an extremely simplified neural network which has only 3 layers, that is, one input layer, one hidden layer, and one output layer. Although a normal neural network, similar to the one you can see here, has only one input layer and one output layer, the number of hidden layers and the nodes in each layer will be much bigger than this simplified one. So how neural networks operate? Normally, it starts with random starting values from the nodes in input layers like x1 and x2 here. It then calculates the value to pass on to next layers as the summations of a simple linear regression function, that is, summations of xi, multiply it by weights wi, and then adding the bias. Then an activation function will be triggered to decide whether the calculated value will be passed on to the nodes in next layer, which is the final output layer in our simplified example here. Let's see how we can train a neural network to build an AI model based on the simple operations we just described. Again, we start with some random values x1 and x2. Then we calculate the output values as mentioned in last slide. We call this process forward propagation. After completion of one cycle from input to output, we use machine learning method to review the results and tune the parameters, that is the weights and the bias. Here you can see that machine learning will based on a predefined target or true value, and the output or prediction value produced by the neural network just now, to calculate the loss score with a loss function. Then we produce a new set of weights value through an optimizer and update each weight values of the neural network. We call this process backward propagation. These forward and backward propagation cycle will iterate until loss score value is minimized, or the model is optimized. Here on the right is an animation of how the weights value evolve after 100 times iterations to help you understand the whole changes process. You can see that the links, which have bigger impact on the final results, are becoming thicker and thicker. You may still wonder how the simple linear regression function can handle deep neural networks' complicated algorithm. The video by Zero Mean 1 Sigma give an excellent easy to understand visualization of the magic. I only clip the part relate to training here for your easy understanding. You are recommended to watch the full video in YouTube.
I have exclusively used these models for a reason, as I consider neural nets to be an extension of linear models. However, before we delve into neural nets, I must make a small adjustment to the way I present equations and write them in the form of matrices. Trust me, this effort will pay off in just a few minutes. Starting with the input vector x, it consists of all the x coordinates of the points in the dataset. Note that I'm using superscripts to indicate the dimensions of the matrices. Next, I'll define the parameter matrix W, which contains only one entry, and the matrix P is constructed similarly. I can then rewrite the equation using these matrices. An output function fx is also represented as a matrix with n entries. The biggest drawback of a linear model is that it's inherently limited by its linearity and cannot effectively fit complex datasets. Neural networks address the issue of linearity in 2 steps. First, the output is passed through a nonlinear function, with the sigmoid function being a very common choice. Then the resulting matrix Z is fed into another linear model with a different set of parameters. This allows for more parameters to be added, making the model capable of fitting complex datasets. Neural networks are highly flexible. and we can increase the number of parameters by simply adjusting the dimension of the matrices W1 and B1. In this case, I've made the matrix 3-dimensional, resulting in a neural network with 10 parameters. We can visualize these equations using a graph structure with several artificial neurons, where the input matrix is represented by a single neuron due to having only one feature, and Z is represented by 3 neurons due to having 3 features. The operations are depicted using connections between the neurons. The same thing is done repeatedly to complete the structure. Training a neural net is very similar to the linear model. We can use automatic differentiation and gradient descent as usual to update the weights. I have discussed these topics in detail and will leave the link of the videos in the cards. What I'm interested in is visualizing how the neural net evolves during training. Considering this dataset and a simple neural network with one hidden layer, we start as usual with a random guess, but you can see that it starts fitting the data points over several iterations. However, it's still not good enough, and the reason for this is that our network can't handle the level of nonlinearity in the dataset. The amazing thing about neural network is that we can make this work with very few changes. Let's increase the number of neurons in the hidden layer to 5. The results are much better now, as we have a model with higher number of parameters to fit the same dataset. There's another way to increase network's capacity, and that's by increasing the number of hidden layers. In this case, with 2 hidden layers and 5 neurons each, the network fits the data perfectly.
Although a real-life neural network will have a structure hundreds or even 1,000 times more complicated than the simplified example we used here, yet the operation and mechanisms are roughly the same. For example, even LLMs like GPT-3 has 96 layers and 175 billion parameters. They all use linear regression, weights, bias, activation function, forward and backward propagation to train their models. I hope the above can help you to understand at least a substantial part of, if not all, how deep neural networks enable the magic of artificial intelligence. If you have any question or want to know more about ANN, please contact our chief consultant, Mr. Rico Chang. Hong Kong telephone number 9082-3965 or email rico.chiang@pr-data.com. Thank you.